P versus NP. This is arguably the most famous unsolved problem in computer science, and actually, if you're cracked enough to solve it, the Clay Mathematics Institute will literally give you $1 million. And all you have to do is come up with a proof for this philosophical question. If you can verify a solution quickly, can you also find the solution quickly? Or in other words, is handcrafting a beautiful meme just as easy as admiring its beauty? To me, the answer seems obvious. Of course, P does not equal NP. Many others believe this, but nobody's been able to prove it. I arrogantly set out to prove that P doesn't equal NP myself and couldn't do it. What's scary though is that if everybody turns out to be wrong and somebody proves that P does actually equal NP, then every password, encryption key, and crypto wallet becomes instantly crackable, while simultaneously curing cancer and ending world hunger. It would be total chaos. In today's video, we'll look at the weird, mind-bending math behind the greatest unsolved problem in computer science, and try to win $1 million in the process. The P versus NP problem was officially defined in 1971 by Stephen Cook in his famous The Complexity of Theorem-Proving Procedures paper, but we can actually go back even further to 1955 when mathematician John Nash warned the National Security Agency that for well-defined cryptography, the effort needed to break a code doesn't scale linear. It explodes exponentially as the key gets longer. He was implying that P does not equal NP, but what's crazy is that there are thousands of papers, decades of research, and zero proof either way. But to understand why it's so hard to prove, we first need to understand the math behind it. P stands for polynomial time, which are problems a computer can solve efficiently even as the input gets bigger. Think about an algorithm that sorts a list of names. As the list gets bigger, it takes longer to sort, but at a deterministic and reasonable pace. When sorting a list of names alphabetically, the amount of work on the CPU is roughly proportional to n or n log n. So if the list gets 10 times bigger, the computer does about 10 to 20 times more work. And problems that grow at a reasonable pace like this are called P. But then things start to get weird when we talk about NP, which stands for non-deterministic polynomial time. These are problems where you might be able to check a solution quickly, but finding it, good luck. Some examples are the traveling salesman problem, Sudoku puzzles, or scheduling your dev team's vacation days. If you already know the answer, verifying it only takes polynomial time, but if you need to find the solution from scratch, you might be waiting until the heat death of the universe. For example, imagine I give you two prime numbers, 7 and 13, then ask you to multiply them together. That's a piece of cake that you could likely do in your head right now. But now imagine this problem reversed. I give you 91 and ask you to find two prime numbers to produce it. You might need to test out a few different possibilities, but you can still do it in your head. But now try the same exercise on 69, 420. What you'll find is that it's far more difficult because you need to explore all kinds of different potential options. And that simple fact is why prime numbers are the foundation for modern public key cryptography, like RSA encryption. Multiplying two primes is easy, but factoring back to the original components is extremely hard. What's funny is that we know it's hard, but mathematicians can't actually prove that it's hard, and can't prove that no faster algorithm exists. Another classic problem like this that you might see on a technical interview is the traveling salesman problem. You have n cities, and you want the shortest route that visits each one once. The brute force approach is to try every possible path, and that gives you a lot of possibilities. N minus 1 bang factorial. For just 15 cities, that gives us like 87 billion different possibilities. That'll make your CPU explode, but here's the twist. If someone hands you the optimal route, you can quickly verify it by checking if it's shorter than the alternatives you already know. Verification is easy, discovery is brutal. Because of that, algorithms in the real world have to be optimized for different rules, or heuristics if you want to sound smart, which aren't guaranteed to get you the best answer, but they should get you pretty close. Basically, you have to trade the optimal solution for a reasonable compute time. So at this point, we know that a problem is NP if a solution can be verified in polynomial time. But there's another special group of problems called NP complete, and these are the worst of the worst. If you can solve any one of them in polynomial time, you can solve all of them in polynomial time. The first NP complete problem was SAT, the Boolean satisfiability problem. Imagine you have a giant logical expression that looks like this. Is there some assignment of true-false values that makes the whole thing true? Checking the answer is trivial, but finding the answer requires tons of different combinations. What's interesting about this one though is that it was the first problem to be defined as NP complete by Stephen Cook in 1971. Since then, many other problems have joined the club, like traveling salesman, Sudoku, circuit design, protein folding, and a bunch of other problems that are really important to humans. What's really weird though, is that they all simulate each other in terms of complexity. And that means if somebody finds a polynomial solution to solving one of them, then all of them will be solved instantly. Hypothetically, if somebody did that, P would equal NP, and the world would completely change overnight. The things that were once impossibly hard are now trivial. But despite 50 years of trying, nobody has been able to find a fast algorithm for any NP-complete problem. In addition, mathematicians have tried to end this debate with a variety of different proof methods, but every time they hit barriers that make it impossible. But why is this problem so important, and why did I even bother to make a video about it? If you really take a minute to think about it, the implications are kind of mind-blowing. If P equals NP, then every puzzle has a shortcut, and the universe is ultimately efficient, like a machine built by an intelligent designer who never wastes computation. But if P does not equal NP, then reality itself contains problems that can't be cut short, like the universe runs on deep computational limits, the kind you might expect if you were living in a simulation trying to conserve processing power. But the scariest possibility isn't that P equals NP or that it doesn't, it's that God or the universe or the simulation already knows the answer, and the entire purpose of our existence is to be the algorithm that computes it.
Let me out! Let me out! I want out!
Unfortunately though, after several minutes of prompting, I still haven't solved the problem, but if you figure it out, let me know, because I could really use that $1 million. Until then, the only thing I have actually solved recently is my backend infrastructure, thanks to MongoDB Atlas, the sponsor of today's video. Everyone's trying to ship new AI features as fast as possible right now, but their backend infrastructure is usually a mess. You've got separate databases for your app data and vector embeddings, a search engine duct taped onto the side, and a bunch of sloppy glue code holding everything together. MongoDB Atlas eliminates all that complexity by providing a modern data platform built for AI applications. You can use it to store all your source data, vector embeddings, and metadata in the same document, then query everything in one place. It also supports real-time stream processing, so your agents can react to live events as they happen, rather than relying on stable batch updates. If you're building an AI app and want to simplify your architecture for good, try out MongoDB Atlas for free at the link below. Thanks for watching, and I will see you in the next one.